in the artificial intelligence group. This was joint work with several commercial providers, including our co-authors at Ubotica and SkyServe. So this work is focused on rapid multi-mission deployment of convolutional neural network and spectral algorithm flight software to do data analysis at the edge. So at the border of the screen, you see some of the spacecraft that we have deployed to and are planning to deploy to. And this is just a subset of the total list that we are going to. The overview of this work is, like I said, we're deploying data analysis flight software to multiple LEO spacecraft, specifically LEO spacecraft that have AI hardware capable of doing neural network execution and so on. So we've already flown and executed on Cognizat 6. This happened back in fall of 2024. We've flown and executed on ION SCV4. This happened about a month ago. We have more flights planned on both of these spacecraft as well. We have delivered our software to the provider of YAM6, so these flights are imminent, and we have several more planned flights on other spacecraft. So why at NASA are we interested in doing data analysis at the edge? Well, at the very least, when we can rapidly obtain insights from data, we can do rapid alerting. And this would be useful for things like alerting to natural disasters, so stuff like volcanic activity, flooding, active wildfires, or harmful algal blooms. And this is made possible both by having the capability to do this on board and inter-satellite links for near instantaneous alerts. So satellites can communicate small data volumes near instantaneously. So the focus of this work is really on, in this workflow, steps 2 and 3. So how we've been able to deploy rapidly to many spacecraft to do onboard data analysis for many different applications. But looking ahead beyond what we want to do with this technology is we can actually leverage this knowledge on board to do more intelligent stuff. So things like optimizing how a spacecraft uses its resources and even takes observations. So there's reactive methods. So this would be where a spacecraft reacts to an observation it's already taken. So this would be something like analyzing an image to see if it's cloudy, and if it is, reject it, and you can remove it from memory and you can save resources. The next step is then to do proactive methods. So we call this dynamic targeting. And this is where a satellite can look ahead at the upcoming environment and actually optimize where it's going to point its sensor. So this would be doing stuff like cloud avoidance, so seeing where the clouds are and then moving the sensor to take a cloud-free image, or even hunting for other things. So hunting for like deep convective ice storms or volcanic plumes. And so now we're not just saving storage and downlink, but we're also optimizing time and energy. So in terms of what's been done at JPL before, and specifically in the AI group, so there's a good amount of AI flight software in operation. So the first flight of machine learning was on EO1 all the way back in 2004. There's been more recent stuff on AVERS and EMIT to do cloud screening. There's been data analysis software on both IPEX and Asteria. These were CubeSats. And then in terms of the Mars rovers, there's the AEGIS system that identifies rocks to sample. And there's also onboard planning and execution systems for the Perseverance rover and the Cadre rovers that are going to the moon. So these systems are great and they work really well, but they have very extensive development, verification, and operation costs. So we're talking years from conception to implementation to testing, and also large teams of people required to operate them. On the flip side, some of the ground workflows that the AI group has developed have been used for rapid response. And so we call these sensor webs. And so these automate the process of downloading data from satellites, analyzing them for stuff like volcanic activity, and then triggering follow-up actions. Now, the real downside here is that there's this huge latency between when the data is actually acquired and when it gets analyzed, and then another latency to then when the follow-up actions get executed. So by doing some of this stuff at the edge and on board, we can reduce that latency quite a lot. So the ability to do this data analysis at the edge is really enabled by an increase in hardware capabilities in space. So many LEO spacecraft now have VPUs that are capable of doing stuff like computer vision, algorithms, image signal processing, and neural network execution. I mentioned before, they have inter-satellite links that are able to do persistent communication. And we also are seeing increasingly capable CPUs and also an increase in RAM. And we're not at the level, obviously, that the ground has, where you have a server with terabytes of data, but we're able to do more advanced stuff on board. So here on this slide, you see these are 3 VPUs that we've been deploying to. So Myriad 2, Myriad X, and Jetsons. And in addition to the hardware, the software environments that we've been deploying to on these LEO spacecraft are also becoming increasingly friendly. And specifically for machine learning, having the availability of modern software libraries in Python enables a lot of quick and easy development. So having packages like TensorFlow available allows us to use the already created architectures and stuff that we want to then deploy on board. So while this sounds great, and now we have ability to all this Python code, it's not as easy as just picking out your code and putting it on board. So for all these spacecraft that we've been deploying to, we have a lot of different constraints. So stuff like having different instruments and data products, having different software versions and hardware, and then different constraints regarding RAM usage and uplink and CPU usage. And in addition, we also want to deploy different algorithms for different science applications to the same spacecraft. So doing stuff like cloud detection versus flood mapping versus volcanic activity detection. So at the bottom of the slide, this sort of illustrates the pipeline that we've been running on board and some of the different, all the different variations that we encounter. So regarding the input data, we have spacecraft that have hyperspectral push broom instruments with maybe 31 channels of data at a very high resolution versus an RGB camera that has a very low resolution. So these data products look very different. In addition to the pre-processing, there's different Python versions, different RAM constraints, and then the models actually get executed on different hardware. So the solution that's been working very well for us and we've been able to rapidly develop for different spacecraft is to have highly reconfigurable software. So what this looks like is we have a parameterized core software suite, and this is where we have the neural network architectures and skeletons of flight packages, but that are highly parameterized, and we get from providers spacecraft-specific information. So stuff like details of the flight environment, details of the input data, and we're able to parameterize our core software suite by using stuff like JSON files to then quickly go from this skeleton to a flight package that we can then deploy to a spacecraft and quickly get to V&V and deployment. So what does this core software suite actually look like? So we've been focusing on convolutional neural networks and spectral algorithms for doing the data analysis, and I'll talk more about what these look like in the next couple slides. But these are parameterized based on the specific satellite that we're deploying to. So stuff like what operations can we do on board? What pre-processing steps does the data have, or do we need to do? What sort of file formats are we interacting with? There's details of the input data, so stuff like what's the dimension of the data, what's the bit depth, what's the resolution, and then, like I said, there's also different applications. So are we doing cloud detection? Are we doing surface water mapping, or all the other applications that we've been looking at? And then to complement these data analysis algorithms, we also have memory-safe pre- and post-processing scripts. So these are traditionally what we're going to run on the CPU, whereas the CNNs and spectral algorithms are running on the VPU hardware. So the memory-safe scripts, these are doing stuff like tiling, scenes, computing covariances and means, which are necessary for some of these spectral algorithms. And we also have stuff to do dynamic band alignment on board. So this is using algorithms like SIFT and ORB. And so we've developed these scripts to have very limited dependencies so that we can deploy them pretty seamlessly to any environment that we encounter as long as Python's available. So in general, what this looks like is we create a configuration file that has all the details of the spacecraft and the environment and the application and what we want to do. We'll have training data as well. So for convolutional neural networks, this might look like image label pairs. For the spectral algorithms, we might have a library of spectral signatures, and then we have automated the process of going from this input to then having a trained algorithm or a fitted algorithm that we can then deploy on board with all the pre- and post-processing. So for the convolutional neural networks, we've been focusing on 2 UNet architectures, and these are doing semantic segmentation. So they are outputting a mask of the classified pixels. So stuff like, is the pixel a cloud? Is it a water? Is it an algal bloom? Stuff like that. So we have 2 models. These are exception and UAV SAR. That's what we call them. They're based on UNets, and they're quite small. They're around 4 megabytes each when compressed. And we've actually been able to chain the executions on board. So we've been able to have, for example, 5 models get executed back to back to back on board. And we haven't run into any issues of having a 4 megabyte model. This has been within the constraints of all the spacecraft we've been deploying to. But there's a huge space of convolutional neural network architectures and applications that you can deploy on board. So we've really only scratched the surface, and we've only scratched the surface of both applications and what these are capable of. So we've been focusing on image segmentation, but you could also do object detection or other things. We even talked about using, We even talked about using neural networks to do stuff like band alignment as well. For the spectral algorithms, so these are primarily doing signature detection, and we're looking at unmixing of high dimensional data. So the core algorithms that we have are spectral angle mappers, matched filters, and read-GLE anomaly detectors. More recently, we've been looking at some other algorithms to do unmixing. But these are more traditional algorithms that are meant to be, or traditionally executed on CPUs, but we've engineered them in a way to use tensor operations to actually leverage the AI hardware on board. And so here you can see just a sample of what some of these look like from past research at NASA for both AVERIS, and this is analyzing a high dimensional input cube, mostly using linear algebra. So in terms of the completed demonstrations that we've done for Cognizant-6, like I said, we executed back in the fall of 2024, and we've had some more execution since then. So we flew convolutional neural networks for cloud, surface, water, and thermal activity detection. We had our 2 unit models for each of these applications. This number has actually grown from 30 plus since these slides were created. I think we're now at over 50 executions. So here are some samples. So on the left, you can see this happened in November. This was during the tragic flooding in Valencia, Spain, and Cognizant-6 took an image and on board was able to classify the water extent in the image, and you can see that there's some flooded area near the top of the image. More recently, in Los Angeles in January, when there was the tragic fires, this was from our cloud detection model. It was able to classify the plumes of the Palisades fire. The current status for the Cognizant-6 flights, this is also actually about a week old. We actually did fly the spectral algorithms a week ago on Cognizant-6. So we flew the spectral angle mapper, matched filters, and the read-GLE anomaly detectors for several applications, including vegetation mapping, which is what you see here. We also flew for cloud detection, surface water mapping, and mineral detection, and some other ones as well. So we're going to be doing more of these demonstrations on Cognizant-6. What we're really excited for is the next step is to do dynamic targeting, which we're actively working on. So for Cognizant-6, what's going to happen is it's going to slew its sensor forward to take a look-ahead image of the environment. And then in real time, this image is going to get analyzed to look for clouds, so identify where the clouds are in the scene. And then the spacecraft will move its sensor to take a cloud-free image. And this whole pipeline is going to happen in around 90 seconds during an overflight. For other spacecraft, we've executed on ION SCV-04. So we had the first executions back in February. We've had a second execution since then. So you can see some samples of these down at the bottom of the screen. So on the left, this is the cloud classifier. And so this cloud mask that you see from this image is actually what was downlinked by the spacecraft. So this is what it obtained on board. And same with the image on the right. So this is doing anomaly detection on board. This is what was downlinked. So for this scene, the spacecraft identified an off-limb acquisition and identified an anomalous limb of the Earth. So we have more flights planned for both ION-SCV and EM6. So these are both ongoing. We have many more upcoming demonstrations. So these are going to be deployments to more spacecraft. This is part of a NASA ESTO effort. So some of these spacecraft include Ares SN1, PhiSat-2, Cagnini-1, and many more. And we're excited for the next step, which is a project called FAME. So this is going to be the largest in-space demonstration of AI to date. And we have over 50 spacecraft that are going to be involved in some way. And so this is going to be both leveraging the onboard data analysis and multi-asset coordination to do stuff like spacecraft triggering other spacecraft observations or doing dynamic targeting and coordinating spacecraft across different operators. So this is pretty unique, and we're very excited about this. And I'll also talk more about this on the next slide. So how we've approached this rapid deployment of data analysis, we've seen a little bit of a shift in how we can deploy code in languages such as Python, for example, and the ease of development for deploying to some of these commercial spacecraft. And so what we really see is end users, so people like scientists and consumers who are the ones developing or who really have the stakes in these data analysis models. So for example, a scientist creating a model to identify some Earth process that will then be identified on board. Given the tools, so given like, for example, a container with the details of the flight environment, they can develop their own Jupyter notebook, for example, to execute their workflow and then plug and play on the vast suite of spacecraft that could then run that notebook. So this is playing into the FAME demonstration. So on this diagram on the right side, we are going to be having users submit workflows. So this might be a scientist that says, I want to have daily monitoring of all the volcanoes on Earth. And if any of them is detected to have thermal activity, then I want hourly observations of it. And so a workflow like that, there's both the data analysis aspect of it, which is to detect thermal activity. And there's also the multi-agent coordination of it. So what satellites are going to be observing the volcano and when. And so all of this is going to be in FAME, and we're going to be using technologies such as cross-queuing and self-queuing, where satellites are able to intelligently plan where its sensor is looking, or I tell another satellite that it needs to take an observation. And so these are leveraging this data analysis that we're doing on board. So in conclusion, the capability of edge processing in space, specifically for image processing and specifically in LEO, has drastically improved in the last couple of years. And we've been demonstrating how we can rapidly deploy convolutional neural network and spectral algorithms to numerous spacecraft. And we feel that the future of flight software for data analysis can be agile, efficient, and innovative. And we're excited about how this could improve the return of Earth observing satellites. And FAME is one example of how we feel that could happen. So that's the end of the presentation. I'm happy to take any questions now.
Thank you very much, Itai. So let's see, we have a couple questions here in the room.
The question on the FAME, is that a 50+ satellites, all different satellites or the same?
These are different satellites. So for example, all of these satellites you see listed at the top of the screen are going to be involved. We have constellations of satellites that are going to be involved, for example, planet constellations. Does that answer your question?
All right, another here from the room.
Hi, I have a couple questions. The first one, I was curious on how you divide what's going in your pre and post processing scripts. Like, are they model specific? Are they common operations? Is it pretty modular?
Yeah, so it's pretty modular. So we have, for example, a script that does tiling. So you can input the parameters that you want to. So for example, how large you want the tiles to be. And this will tile a scene and it'll output, and you can configure, what files to save it as, for example. And we also have other stuff like, based on that, can we compute covariances and can we compute means and stuff? So it's very modular. We can take from these the operations that we want to do and quickly compile them into, a larger pre-processing pipeline. On the post-processing side, usually what this is either doing some sort of compression for downlink, or for satellites that have ISL capabilities, we've been sending messages that have summaries of the data obtained on board. So for Cognizat-6, these experiments, after the data is analyzed on board, we post-process it and it obtains basically like an abundance. So it'll say, X% of the scene that I just acquired was clouds, and then it sends that as a ISL message, and we obtain that on the ground very quickly.
All right, before we take any more from the room, there's one on Slack by Joshua Ross. He asks, what is the order of latency between image in to processed output for simple RGB cameras?
So this is entirely dependent on the spacecraft. So in terms of how long it takes our software to execute, it's quite quick. So the whole pipeline, we're talking on the order of minutes, but it could be as fast as the order of seconds. So most LEO spacecraft were not designed to need to do this data analysis so quickly, but for some of them, that is intentional. They did include that in the systems design. And on these spacecraft, we're talking about seconds from image acquisition to image analyzed. And actually for the dynamic targeting experiment, which I think is right here, so this whole data analysis pipeline is happening in an overflight. And we have about 90 seconds from look-ahead acquisition to when we want to take a near-nadir acquisition. And so that 90 seconds is the time that we have to analyze the incoming scene.
All right, any more from the room? We got one more here for you, Itai. Just hold on tight.
Hello. So how low were you able to get the bit precision for inference? So 8-bit is common, and so Microsoft released a large language model that's down to 1-bit. So how low were you able to get these convolutional neural network precision?
Yeah, so we've mostly been executing in floating point 16. Now, this is not necessarily the case. It's not because we have to. It's because we want our models to be quite small, and then we've been able to do stuff like chaining model execution, so we can run 5 models in sequence, versus if you have a larger model, you may only be able to run 1 at a time. So again, I think this is somewhat spacecraft specific, is what the constraints are of the spacecraft requiring how large can your model take up in RAM. Yeah.
All right, and the last question here from Slack, from Ty Ellison. Can you speak a bit more about the process involved going from algorithmic insight on one spacecraft to federated scheduling to executing scheduled commands on other satellites? Thank you.
Yeah, so what this looks like, so for example, federated scheduling is the process of autonomously coordinating the assets controlled by different operators. So for example, you may have a Planet spacecraft and a Eubotica spacecraft, and a Eubotica spacecraft takes an image that has clouds, and we needed a cloud-free image. So now the next soonest available overflight is on a Planet spacecraft. So the idea is that we can actually coordinate these using federated scheduling, which is basically asking Planet to schedule that overflight. And so most commercial providers now have electronic interfaces where you can request specific overflights to be executed. So that's kind of how it's going to work. So for example, you could imagine the Eubotica spacecraft takes an image. On board, it in real time detects that the image is completely cloudy. And so it would send an ISL message to the federated scheduler, which would then trigger that it needs another observation for that location, and it would look at the available overflights and then automatically allocate that, or maybe it would allocate it to multiple spacecraft, so that sort of thing.
All right, perfect. A round of applause for Itai. Thank you.
All right. So we are actually going to break for lunch now. So there's going to be a handful of us. Look for a green badge if you want someone to fearlessly lead you through campus. Otherwise, there is on the announcements, there's actually a map. We are going to the Hub Lyceum Ballroom. Food is waiting for you. So please basically pack up your stuff. We are not coming back to this room or this hall today. We will be back here tomorrow. But if you want any of your stuff, take it with you. And we'll see you in the ballroom. Thank you so much.
For those online, we're essentially going to go offline for a couple of minutes while we move over. And then once we're in that room, we'll go ahead and get set up. So we'll be back with you shortly. Thank you.